Okay, welcome everybody. Let me first introduce myself in brief. My name is Mustafa. I have been here in Baffinland for around 3.5 years. I've joined in
Talking loud.
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 Okay. I joined Baffinland in 2020, and I worked in reliability department and planning, and I previously have some experience in steel industry and for about 10 years, and about 4 years in forest industries, 2 years in a sawmill and 2 years in a paper mill. I have a bachelor degree in mechanical engineering and a graduate diploma in engineering management. I am a professional engineer in Ontario, and I hold some certifications in maintenance, reliability, and project management. So before we start, does anybody has a safety share?
Sure.
Yeah.
I don't know if people noticed, but the wind's picked up a lot since this morning. Time to get off the bus. So just be aware of that. Careful, it's not that the wind's blowing, it's what's blowing in the wind. So keep your eyes out and be alert. You don't end up getting hit by something.
Okay, thank you, Alan. So today we're going to talk about Industry 4.0. We're going to give a brief introduction about the industrial evolution, some definitions and origins of Industry 4.0, and some key concepts about it, the design principles, the benefits and challenges, and the building blocks or the main technologies used in Industry 4.0. And then we're going to talk about two important concepts, cyber physical systems and IoT, and then the IIoT, the industrial IoT. And then we're going to give some examples about the application of IoT and industrial IoT. And then we're going to talk a brief about horizontal and vertical integration. And then the application, this is like what it has for us in mining industry, the application of IoT in mining, and then some of the challenging of using IoT in mining, and then we're going to give some real life examples. So basically, industry before the 18th century, industry used to be very primitive, very simple. It used to be in houses or small shops and using hand tools and very simple mechanisms and stuff like that until the middle of the 18th century, when the first industrial revolution took place, which was characterized by the mechanization. So it introduced the mechanization of production using water and steam energy to increase the production and the productivity. So and the year 1784 marked the first mechanical loom. And this phase took about a century until the end of 19th century and beginning of the 20th century, where another evolution took place, which was called the second industrial revolution, or the industry 2.0, which was mostly characterized by the electrification, which introduced the labor-based the labor-based mass production, which was or the assembly lines that is powered by electricity. And the year 1870 marked the first production line in Cincinnati slaughterhouse. And this phase also take about a century or a little less until the start of 1970s, where the third phase took place, which was called Industry 3.0, which was mostly characterized by automation, where electronics and computers were introduced to replace the manual work using standalone robotic systems. And the year 1969 marked the first PLC, or programmable logic control. This also took place for many decades until recently, close to that 2010, where the fourth industrial revolution, or the Industry 4.0, which is mostly characterized by what is called cyber-physical systems. We're going to discuss this concept later. So it's the conversion of physical, digital, and virtual environments through the CPS and the IoT, the Internet of Things. So some definitions and concepts. The term Industry 4.0 was originated in 2011 in Hanover in Germany. It was known as Industry 4.0 in Germany, Connected Enterprise in the United States, and Fourth Industrial Revolution in United Kingdom. So like different words for the same concept. And it can be defined as a smart industry, which refers to technological evolution from embedded systems to cyber-physical systems. Okay. So we can also say that the current trend of automation of data exchange in manufacturing technology, including the CPS and the IoT. Industry 4.0 is an example of connecting the different physical devices using the embedded electronics to a network or internet. So it can be either an internal network or the internet. So these devices can interact, whether it's man to machine or machine to machine, using the mass or enabling the mass customization of manufacturing. So the last thing here is it's important, or the Industry 4.0, it is important to implement horizontal and vertical integration, and we're going to talk about this in the next slides. Okay, there is 6 principles for design of Industry 4.0. The first one is interoperability, which is the ability of the cyber-physical system and humans to connect and communicate with each other via the Internet of Things. So just a small example, like maybe many of us have this smart thermostat at home. So this is an example of IoT, where you can see that your system is working, and you can turn it on and off and adjust the temperature on your cell phone, and it will operate the system that is thousands of miles away. And the same thing, if someone changed the temperature on the thermostat, you can see it on your cell phone. So it's a kind of interchange or interoperability between the computerized system and the physical system. Second characteristic or principle is the virtualization. So you can see a virtual copy of the factory or the system by linking the sensors with a simulation models. So you can see a copy of your plant in your computer. The third concept is this decentralization. So it's not only about that you can control a system from remotely or from a device. The system itself has the ability to make decisions on its own. So let's say if there is leakage in some valve or something, the system can sensor and can shut off a valve for safety and for preventing accidents or damage to the system. The real-time capability. So this system is not about collecting data and analyze it offline. It's about real-time interaction between the computerized system and the physical system. Service orientation, the ability of the system to offer services. So just an example away from this or away from industry, like the mobile banking. You have an application in your bank that you can, on your cell phone, that you can make transactions on your bank, and this is an example of the Internet of Services, that the system has the ability to make services. The last one is the modularity, which is the flexible adaptation of the smart factories for changing requirements of individual modules. So let's say that we have in our mine here, we have mobile equipment and we have fixed plant. So we can have one integrated system that deals with everything in the mine, whether it's mobile or a fixed plant. And even the fixed plant are different. Even the mobile equipment are different. So the system has this flexibility to adapt and work with different kind of equipment and systems. So any questions so far? Okay, so this concept of this revolution can truly improve the manufacturing process, but also there is some disadvantages or challenges with it that comes with it. So some of the benefits is the optimization of the production and the supply chain, the improvement of efficiency, the flexibility and agility, the improvement of production quality, better customer experience, reduced cost and increased profitability, and last thing, the enhanced potential for innovation. Some of the challenges include the data and IT security. We are talking about computerized systems and data transfers and networks, so a lot of security concerns that has to be addressed. Capital investment, we are talking about devices and sensors and software and licenses and training for the people, so all this includes capital investment. The lack of skills or the need for qualified personnel to understand and work with these systems. The culture change, the culture challenges, applying a new system or a change, it always a big concern. And the lack of digital infrastructure, especially if we're talking about mine in a remote area that there is no, you need to build the infrastructure from even like from scratch. Okay, the building blocks. This is some of the technologies that are used in Industry 4.0. This is not everything. This is just some examples, like the robotics, the simulation, the horizontal and vertical integration, the industrial IoT. This is one of the main things we're going to talk about in more detail. Cybersecurity, cloud computing, additive manufacturing, augmented reality, big data and analytics. There is also the drone. Drones are one of the big things in here. The AI, the artificial intelligence. So this is just some examples. So we mentioned a lot the cyber physical system. What is it? It is a system of calibrating computational elements, controlling physical entities. So the cyber physical system consists of some physical components and some cyber components. The physical, like the sensors and the actuators, the cyber components like the computing, the storage, the communication. So connecting the physical assets with computerized systems, using the IoT technology. So the CPS is the frame or the system, and the IoT is the technologies that is used to apply this system. So the IoT is the intelligent connectivity of physical devices, driving massive gains in efficiency, business growth, and quality. So this is the IoT. The IIoT or the industrial IoT is simply the using of the IoT technologies in industry. So that's which enhance the manufacturing and industrial process. Some of the examples for IoT, there is many examples, but this is just a brief about it, just a small example. The smart buildings. So as we talked about the thermostat, this is one example. We can use also some power meters, gas meters, temperature sensors, humidity, and these are all connected to the internet or the network that is connected to a computerized system that can control the whole building or the whole complex of buildings, so that it enhances security and safety of the people living in these buildings. So in case of gas leakage or something, the system has the ability to cut off the gas, or also in case like of fire or something, it has the ability to give the alarms, to give to operate the fire suppression and stuff like that. In sports, for example, the company Populat has the tennis rackets that has sensors in the handle, which allow the users to track and analyze ball speed, the spin, and they can analyze this data to improve the play. In soccer, for example, you might have seen some players wearing this vest. This vest has sensors and trackers that can that has a GPS that can measure the distance, the kilometers they do in a game, and can also measure some of the biometric information about the player, and also it can be some sensors and devices can be put in the cleats, and these systems can be connected to like a mobile device or computer, and maybe so the coach can be sitting on the bench watching his players and see like the heart rate. I can see the biometric about his players to track if anybody has any medical issue or anything, or on the long run to analyze the performance of his players. This was the IoT. So the IIoT, the industrial IoT, one of the main applications is the smart manufacturing. So the plant is connected with sensors and other devices that connect all the parts of the plant together, and also connect the plant to the main office of the company and the ERP system, and also connect it to distribution centers and customers, and even to the supply chain, and even to the power grid. So and talking about the smart manufacturing or the smart plant, we must talk about the horizontal and vertical integration. So basically, the horizontal integration is the integration and between the plant and different plants or different factories for the same company maybe, and also the integration with the warehouses and customers and the suppliers. So all of this is horizontal integration, but also the IoT or the IoT and Industry 4.0 allows for or enhances the vertical integration, which is the integration between different levels of management, starting from the corporate level, the operational level, the process management level, and down to the floor or the field level. Okay, before we go to the mining section, any questions so far? All good? Okay, so what is the application of IoT in mining? There is many applications. We're gonna talk about 6 of these applications. So the first one is the autonomous mining equipment. So the IoT enables autonomous equipment and vehicles which make the mining safer and more cost efficient. Examples for the autonomous equipment are the self-driving trains, the remote-controlled equipment, and the tele-operated equipment. So basically, the main difference between the remote-controlled and the tele-operated is that the remote-controlled needs the operator to be in close proximity to the equipment, while the tele-operated can be operated from a different site, which could be hundreds of miles away from the mine site. So this increases the safety of workers in case something happened to the equipment. At least the operator is safe. The IoT wearables is another example of the automation or the autonomous equipment. Many a big range of wearables devices can be worn, like smart glasses, smart watches, GPS, Bluetooth tracker, smart shoes, smart bands, smart ring, smart bracelet. So a lot of smart things that can have track the location of the worker, and also track some of the physical and biometric condition of the worker. And this is very important, like especially for people who are working, who has to work like in their own, so not accompanied by other workers, and people working in confined spaces and in underground or places where there is emissions or gases or fumes. So these devices can detect where you are and detect if there is anything in the surrounding environment that can harm you, and gives the alarm to the appropriate department or responsible. Another example or application is the location at the proximity sensors, which can help avoid accidents in mining. Using some stuff like GPS, the radars, RF, the radio frequency locating technologies, to detect the proximity of heavy equipment or vehicles to each other or to people. So this can affect improve the safety, which is directly proportional to the company's profit. So just an example of an equipment that has those sensors that can detect if anything is in proximity, and gives alarm to operator and other equipment besides, so it prevents accidents and such things. The next application is the on-demand ventilation systems, or VOD, or ventilation on demand. So this is very important, especially in underground mining, but also in open pit. It can be useful in places like incinerator or sewage plant, where there is a potential for gases or fumes. So basically, if we have a place like this that has 3 compartments, if we don't have a smart system for ventilation, all compartments will have the same amount of ventilation. But with smart ventilation system, we will have adequate amount of ventilation for each room depending on the requirements. So this room has only 1 person, has only adequate amount of ventilation. This room has many people, so it has more ventilation. In mines, especially in underground mines, there is the ventilation network, which gives a map of the ducts and the ventilation ducts all around the mine. And the way it works is there is sensors. In different locations that detect the conditions and gives the information to a centralized room or control room, which gives the fans and the ventilation devices the order to provide adequate amount of ventilation to the place according to the requirement. The next application is the sensors for predictive maintenance. So basically the predictive maintenance depends on condition monitoring. So the condition monitoring can be done like manually using detectors like vibration devices that can collect the information and then analyze it offline. But this is the traditional way. The new way is the online monitoring or continuous monitoring using these technologies. So we have a machine that has sensors on it that can measure different parameters. Maybe the vibration is the most or the most common technology used in predictive maintenance, but there is also other stuff that can be measured, and then it will be sent to centralized devices that can analyze and gives real-time insights for the reliability engineers um, and allows for early detection of any defects, so that we can take actions before a failure, a significant failure, take place. The next one is the fleet management and tracking capabilities. So with the technologies like micro tracking, using 5G and other technologies, we can track the trucks and equipment from a central office, and the efficient tracking of equipment can reduce the theft instance, wastage, illegal entry, and so on. So it saves money and ensure the safety of workers. So we can install devices that detect the information or the location of all the equipment we have, so we can achieve all these benefits and help the dispatch, and it helps also maintenance. Like for example, here we have two locations. We have the port, and we have Mary River, so sometimes we are not sure where the equipment is. So if we know exactly where the equipment is, we can schedule the maintenance in the right place. The last one we're going to talk about is the visualization software. So with the IoT technologies such as GPS and sensors, we can build a 3D map for the mine. So the mine engineers and drill and blast teams can use this map to better understand the layout and the navigation and the operation management and troubleshoot any emergencies. So there is many softwares that are used to visualize the mines, like different softwares that are available, and gives you a full picture of the mine, so that we can analyze and control the mine. So we talked before about the challenges, but there is some specific challenges in the mining industry for applying the IoT, such as the connectivity challenge we talked about, and it is very significant in mines, especially in remote areas. And the second one is the different stands on IoT deployment. So until now, there is no consensus between even the big mining companies about whether using the IoT is the appropriate or not. Because some of the big companies don't see that it is very applicable or appropriate for the mining industry because of the fluctuation of the prices and the instability in the mining industry. But other companies took big steps on applying these technologies. And the third challenge is the hassles during the project execution that we talked about for the communication and the security and the human factors and all this stuff. So the last part, we're going to talk about some real-life examples for applications of IoT. So the first one, it's for monitoring the underground operations. So in Glencore, they used a system called the NewTrax to monitor the mine and provide insights on the underground operations. The biggest challenge they had was the long haulage distance between trucks. The trucks had to travel to deliver ore from the mine. So as a result, they wanted to optimize operations by maximizing the load. So they applied this system on its fleet, and their engineers started to monitor the production times of the individual equipment and calculate the utilization and the load per cycle to improve the mine efficiency. And through applying this system, they were able to increase the load per cycle by 5%. They were able to increase the average tonnage of ore pulled during each outing from 55 to 60 tons. And they were able to increase the overall equipment effectiveness and productivity. The second one is about the application of IoT in predictive maintenance. So this company, Cortez Mine in Nevada, they had they relied on a maintenance on-demand approach, which is mainly a reactive approach. So basically, they have like the PMs or the periodical maintenance that is done on certain cycles, but between these cycles there is no way to detect the condition of the machine. So failures can happen, and which lead to high cost and may cause safety implications. So they applied this system to enhance the asset health monitoring for 34 trucks, whole trucks, and the main goal was to improve the maintenance efficiency. So basically, it's about installing some sensors that collect data from the engines and from different areas or different systems of the equipment, and send it to a centralized system that can analyze and gives insights about the condition of the equipment, so that we can interact quickly before a failure happens. And by utilizing this system, they managed to save 500,000 each month due to the ability to detect and address the failures proactively, and reduce the total number of equipment failures by 30%, and achieve about 600,000 in saving from single early fault detection for one piece of equipment. The third example here, it's also about predictive maintenance. So this one of the global mining companies. They already had a system for predictive maintenance, but it was more of a manual system that used to collect information and analyze it like offline. So they started applying this system, which we call Litmus, to collect. This system collects data directly from PLCs and sensors. Then it analyzes the information related to machine running parameters. So, and finally, the system sends real-time alerts to the engineering team, and these alerts enable them to identify the deviations early and take preventative steps. And by applying this system, they were able to avoid the cost of unplanned downtime, estimated at $1,000 per $100,000 per hour, improved the business efficiency by 20%, and increased the return on investment by a quarter. The final example I have here is about VOD, or the ventilation on demand, applied by Goldcorp. So the VOD system they applied consisted of sensors, AI algorithms, and an interface. The first thing, the sensors collect the data about the ventilation condition. Then the algorithms analyze the ventilation requirements in the zone, and based on this analysis, the system can adjust the fan speed and fine-tune the ventilation. And this helped to provide the correct amount of air to areas where it is needed. And by applying this system, Goldcorp was able to cut the electrical consumption by half and reduce the cost by about 20%, and reduce the air intake by half, almost half, from 1.2 million cubic feet meter to 0.65. And that was it for me. Any questions?